This video is on section 5.4 notes, the other trig functions and their graphs. So before we talked about sine and cosine, but we know there's also tangent, that's why you hear SOHCAHTOA. And then there's also the reciprocal functions, which are cotangent, secant, and cosecant. And so we're going to talk about the other four trig functions aside from sine and cosine today. So here I'm going to draw my right triangle in my unit circle. So I dropped a line from the point straight down. If this point is xy, then this side of the triangle is a length of x. This side of the triangle is a length of y. And this side of the triangle right here is a radius. And so in the unit circle, it's a length of 1. And we know that for all of these, we're finding the different trig functions for angle alpha, this angle right here. So I'm going to find sine alpha, cos alpha, tan alpha. And then I'm going to find each of their reciprocal functions, which is cosecant, alpha, secant, alpha, and cotangent alpha. Okay, so sine is the opposite side over the hypotenuse, opposite over hypotenuse. Which is y divided by 1, and that's just y. So we learned that before. Cos is adjacent over hypotenuse, adjacent over hypotenuse, which is x over 1, and so that's just x. And then tangent is the TOA, so this is SOHCAHTOA. Opposite over adjacent, and opposite over adjacent is y divided by x. So when I'm talking about the x and the y divided by x, I'm specifically referencing which coordinates on the unit circle are going to be used if you have sine of an angle or cos of an angle, which we've already practiced, but now we know how to do tangent of that angle. So if I want tangent of pi over 6, I just do the y coordinate divided by the x coordinate. Now, these are the reciprocal functions, and so you just take the reciprocal. Instead of opposite over hypotenuse, it is the hypotenuse over the opposite side. Instead of adjacent over hypotenuse, it's hypotenuse over adjacent. And instead of opposite over adjacent, it's adjacent over opposite. And so here, instead of thinking of this as y divided by 1, it's 1 divided by y. And I don't like thinking of it this way. I just think of it as the reciprocal of the y coordinate, or just take the y coordinate, the fraction that is the y coordinate, and flip it. Here, this is x, or x over 1, and so secant of alpha is 1 over x, or you can just take the reciprocal of x, take the fraction that created the x coordinate and just flip it. Cotangent is adjacent over opposite, and so adjacent over opposite is just x over y. I'm going to go ahead and write each of these in, x over y, y over x. So if alpha is an angle in standard position and xy is the point of intersection of the terminal side and the unit circle, we define the other four the other four trig functions this way. All right, so it says find the exact values of all 6 trig functions for each angle. So first we're going to find sine of negative pi halves, and then cos of negative pi halves, and then tan, and then cosecant, then secant, and then cotangent. Okay, so on my unit circle, negative pi halves is just measuring backwards pi halves. So negative pi halves is down here. And so sine is the y coordinate. Cosine is the x coordinate. Tan is the y coordinate divided by the x coordinate. So that's -1 divided by 0. And -1 divided by 0 is undefined. Cosecant is the fraction that you would write sine as, and then you take that fraction and you flip it. So sine as a fraction would be the number -1/1. That's that whole number written as a fraction. If I flip it, I get 1/-1, and that is still just -1. For secant, we take cos, we think of it as a fraction, so 0/1, because anytime you have a whole number, you just stick it over a 1. We take that and we flip it, and that would be 1/0, and so secant is undefined. Cotangent is just tangent flipped. I wrote undefined, so I don't, maybe I don't remember what tangent is. So the other way to do it is to just take this and do x divided by y. 0 divided by -1 is just 0. Okay, so there's my 6 values there. Next, I'll do all 6 for 5 pi over 6. So sine, cos, all right, so I'm going to look at 5 pi over 6 on my unit circle, and it's right here. Sine is the y coordinate, cos is the x coordinate. So sine is the y coordinate, cos is the x coordinate. Tan is going to take a little bit more work. Tan is the y coordinate divided by the x coordinate. So this is, I'm going to write it down here because I'm going to have to simplify it a little bit. 1/2 divided by -√3/2. And when we have a fraction divided by a fraction, we just take the denominator and we multiply by the reciprocal. So this is going to become 1/2 times 2 over -√3. So the 2's are going to cancel. Divide by 2 and multiply by 2 are going to cancel. And I'm going to zoom in for a second here. All right, so I end up with 1 over -√3. And this is not proper notation. You're not supposed to leave a square root on the bottom. And so I'm going to multiply this by √3 on the top and √3 on the bottom. And so on the top, I have 1 times the square root of 3, which is just square root 3. And on the bottom, I have √3 times √3, which is 3, or you can think of it as √9. So I've got a negative, and the square root of 9 is 3. Okay, so this is what it simplifies to become. -√3 over 3. And you don't have to do this work every time. You just have to remember that when it's 1 over √3, because the 2's cancel, when it's 1 over √3, it becomes this. That's all you got to remember. Okay. Cosecant is sine flipped over. So 1 over 2 flipped is 2 over 1. That's just 2. Cos is going to take a little bit of work, because if we have -√3 over 2, then when we flip it for secant, it's going to be 2 over √3, which is not proper. We can't have a radical on the bottom. So I'm going to write this 2 over -√3 that is not proper. So I'm going to multiply this by root 3 over root 3. On the top, I have 2 times root 3, which is 2 root 3. On the bottom, I have root 3 times root 3, which is just 3. And then I also had a negative. Okay, so this is what secant is. Negative 2 root 3 over 3. Okay? And then for tangent, I can flip this if I want. I would have to fix it. Or I can look in my work and go back and I can choose which fraction to flip. So I could flip the beginning one. That's going to require some work. The fraction that's going to be the best to flip is this one right here. This is the answer before I fixed it and made it proper. And if I flip this one, it's going to be perfect for cotangent. Okay, so if I flip this answer, I can get the right answer. I'm just going to have to do some work. If I flip this one, I'm still going to get the right answer. I just have to do some work. But if I flip this one right here, then I'll have the right answer immediately. So if I flip it, I have negative root 3 on the top and 1 on the bottom. And negative root 3 on the top and 1 on the bottom is just negative root 3. Okay, so there's my 6 answers. All right, next, 4 pi thirds for all 6. So sine, cos, tan, cosecant, secant, cotangent. All right, 4 pi thirds is down here. So sine is the y-coordinate, negative root 3 over 2. The x-coordinate, negative 1/2. Negative root 3 over 2. Negative 1/2. Okay. Tangent is going to be y divided by x. Y divided by x. That's kind of nice this time. Negative root 3 over 2 divided by negative 1/2. Keep the top one. Multiply by the reciprocal. The 2's cancel. Negative root 3 over negative 1. I guess I could have canceled the negatives right here, but the negatives cancel. And I end up with root 3 over 1, which is just root 3. Okay? And now I need to flip, flip, flip. So this one is the negative version of this flipped. And I've already done the work for that. It is this. So 2 root 3 over 3. Okay. Secant is the flipped version of cos. So negative 2 over 1, which is just 2. And then for tangent, I just have to take this fraction and flip it 1 over root 3. I did that over here. That becomes this. So 1 over root 3 is actually root 3 over 3. So there is a point where the answers do get kind of redundant, which makes sense because the unit circle is just a lot of the same numbers over and over again. Okay, it might be a good idea even for you to write down some of the other ratios on your unit circle. I don't know if you want to. Okay, so there's the exact values for all 6 trig functions for each of those angles. Okay, now we have some identities here. So tangent, since tangent is y divided by x, you can also say that tangent is sine divided by cosine. So that's, that's interesting. Since cotangent is x divided by y, you can also say that cotangent is cos over sine. So that's interesting. Since secant was 1 divided by x, you can say that secant is 1 divided by cos. And then since cosecant was 1 divided by y, you can say that cosecant is 1 over sine. So those are interesting. Now, these 3 in particular are pretty helpful. I'm going to write another one for cotangent. The other one for cotangent is that cotangent is 1 divided by tangent. Now, these 3 are helpful because if you've looked at your calculator, you'll notice there is not a secant, cosecant, and cotangent button on the calculator. The only buttons you have are sine, cosine, and tangent. So if you get to a problem like this where it says use a calculator to evaluate these, you're not going to be able to do it unless you understand these other reciprocal identities. Okay, so if I wanted to use my calculator to calculate secant of pi 12ths, I would not click a secant button because there isn't one. I would type this in my calculator as 1 over cos of the angle instead, because it's the same angle. So I'm going to say 1 over cos of pi 12ths. That's what I'm going to type into my calculator. For this one, I can't type in cosecant. I'm going to have to type in 1 over sine. So I'm going to type 1 over sine of 123 degrees instead. For this one, I can't type in cotangent of negative 12.4 radians. I know this is radians because there's no bubble. I have to type in 1 over tan of negative 12.4 radians. And that's how I'm going to get my answer. Okay, so let's go ahead and type these in. My calculator is currently in radians, so I'm going to do the first and the third problem first. So to type this in as a fraction, you can do 1 divided by, that would be fine. Or if you want to click the green button and then the gray button up here, you can type this in like a fraction. So 1 over cos of pi divided by 12. I did that pretty quick, so I'm just going to tell you the pi is right here in blue. And so to get the pi on your screen, you have to hit blue and then this button right here. So cos of pi 12ths is 1.0353. They wanted 4 decimal places, so 1.0353. Okay, I'm going to skip this one and do the one on the end. 1 over tan negative 12.4, 5.9551. Okay, and then for the one in the middle, I'm going to switch to degrees. 1 over sine 1, 2, 3. 1.1924. And this answer that I got represents the ratio of the sides. So secant is the hypotenuse over the adjacent side, so the ratio of those sides is this decimal. The ratio of the hypotenuse over opposite is this. The ratio of adjacent to opposite is this. So that's what those decimals mean. All right. Oh, sorry about that. I don't know if you heard that. I knocked my microphone. Okay, the next page has us starting to graph the other 4 trig functions. So we're going to go through these relatively quick because I'm not going to require a ton of graphing of these other ones, but I do want you to understand how it works. So here's what we need to graph tangent. Tangent works a little bit differently than sine and cosine. It looks completely different. So first, let's look at tangent of negative pi halves. So negative pi halves is down here. Tangent of negative pi halves is the y coordinate divided by the x coordinate. We know that tan of the angle is y divided by x. So y over x is negative 1 divided by 0, and that is undefined. So we're starting off strong with a vertical asymptote. Vertical asymptote, an imaginary line that is not going to be crossed. Okay, then we have negative pi fourths right here, negative pi fourths. Y divided by x, we're taking the same number and dividing it by itself, and so this is going to give us negative 1. Then we have 0. So 0 radians, 0 divided by 1 is just 0. Then we have positive pi fourths. The same number divided by itself is 1. And then we got pi halves. 1 divided by 0 is undefined. We have another vertical asymptote. Okay, so I went ahead and I drew my axes similar to what I did in the sine and cosine video, but I scaled the y-axis a little differently this time just to save myself some time. I drew these ahead of time so the video wouldn't be as long. Okay, so the first thing I'm going to do is go ahead and draw my vertical asymptotes. And what I would say as far as strategy goes for graphing, that having the graphs for sine and cosine memorized is 100% important. You better have those memorized. You should know the patterns. You should be able to do transformations without looking at your notes. For the other 4, I would say graphing tangent, you should be pretty familiar with. But if you are not like perfect at graphing those without notes, that's okay. For the other 3, cotangent, cosecant, and secant, if you cannot graph those without your notes, that's totally fine. You do not need to know them any better than being able to do it with your notes right there next to you, okay? That level of familiarity will be just fine for your next math courses. But for sine and cosine, you better be able to do those without notes because you need to be really familiar with those 2 graphs. Tangent, not quite as familiar, but still pretty familiar. Okay, we got our vertical asymptotes at negative pi halves and positive pi halves. Then at 0, we got 0. Negative pi fourths, we have negative 1. Positive pi fourths, we have positive 1. And so this looks almost like an x cubed graph, except as it grows, it's approaching the asymptotes. So it looks like this. Looks a little bit like x cubed, but then it approaches asymptotes on the 2 sides. So what ends up happening is we have an x-intercept here, and then we have an x-intercept at pi, and an x-intercept at 2 pi, and an x-intercept at 3 pi, and at 4 pi, and at 5 pi, and at 6 pi. So every pi, we're going to run into the x-intercepts. And I can show you why that is. So as we keep doing these points, this is the next fourth, so 1/4, and then this would be 3/4. This is a negative 1, and then we have 1 pi, this is the 0, and then this is the positive 1, and then undefined, and then negative 1, 0, positive 1, undefined, negative 1, 0, positive 1, undefined. And so it follows this kind of rotation through just like we had before. So at all the pi halves, we're going to have 1 divided by 0 or negative 1 divided by 0. And so at all the pi halves, we're going to have vertical asymptotes. And then at all of the whole number pi's, that's where we have 0 divided by 1 or 0 divided by negative 1. And so that's where all the x-intercepts are. Okay, so here's another piece of the tangent curve. There's another one. So now that I have the x-intercepts in there, I can just go ahead and add the other points, the negative ones and the positive ones. Okay, so this is what a tangent graph looks like. So there's a couple of things that we should notice. One thing we should notice is that the period of the graph, or how wide the graph is to get one full piece of the curve, is 4 boxes. And 4 boxes is a length of pi. So the period of this function is not 2 pi like it is for sine and cosine. The period of this function is just pi. Okay, so a typical period is just pi. That means that for us, when we're dealing with the transformations, to find a transformed period of the function, we're going to use the formula pi divided by b. It also means that when we look for the frequency is still going to be a value of b, but it's going to be a value of b on the interval from 0 to pi instead of the interval from 0 to 2 pi. All right? Since these graphs don't have waves, since they just go up and down forever and ever, we don't talk about amplitude anymore. We're not going to ask what the amplitude of this graph is, but you could ask what the vertical stretch is. So we're kind of going back to that language, but we're not going to talk about the amplitude of this graph. So we can still ask the period of the graph. We're going to do pi divided by b. So for me, when I look at this graph and I think about how I'm going to graph this and think about shortcuts, I'm going to recognize that the x-intercepts are the width of the period. So the x-intercepts are at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. And I'm going to recognize that the vertical asymptotes are exactly halfway between the x-intercepts. So x-intercepts 0 pi, 2 pi, 3 pi, 4 pi, because the period is a width of pi, x-intercepts are at pi halves. Okay? One thing that is interesting about these graphs is when you write the domain of the graph. And so I'm going to write this down for the parent function of tangent. The domain is all real numbers except for negative pi halves, positive pi halves, 3 pi halves, 5 pi halves, 7 pi halves, 9 pi halves, 11 pi halves. All of the pi halves you can't have, but they're always 1 pi apart. So the way that we write that is we say all real numbers, you can have all the numbers as long as x is not equal to pi halves, positive pi halves, or any interval of pi halves, 3 pi halves, 5 pi halves. We're trying to write down that interval. So I'm going to say pi halves plus pi k. So that tells us every interval of pi halves that is a width of pi, that gives us that line we cannot have. So every single number except for the vertical asymptotes. Okay, hopefully that was somewhat clear because I feel like my explanation was a little confusing. Let's try the next one. Okay, so this next one, all they did was change the period of the graph. So we do not have a difference in the vertical stretch. We're still going to have the x-intercepts there, and we're still going to be going up 1. So that's going to be normal for the graph. The only difference is that we have a b value of 1/2. The b value here is 1/2. So I'm going to say no vertical stretch or compression. So this is just a 1. The period is pi divided by 1/2. And pi divided by 1/2 is pi multiplied by 2 over 1, which is 2 pi. So the period of this graph is 2 pi. This means that the frequency is 1/2. So for a normal period of this graph from 0 to pi, I'm only going to see 1/2 of the curve. All right, since the period is 2 pi, I'm going to see the x-intercepts every 2 pi. So my first x-intercept is going to be at 0, and then at 2 pi, and then at 4 pi, and then at 6 pi, negative 2 pi. And my asymptotes are going to be in the middle of those. So asymptote in the middle, asymptote. Okay, and then if we look up here, halfway between the x-intercept and the asymptote, we go up to 1. Halfway between the x-intercept and the asymptote, we go down. So halfway between here and here, I'm going to go up to 1. Halfway between here and here, I go up to 1. Halfway between here and here, I go down 1. So go up to 1, go down 1. Go up to 1, go down 1. Go down 1. All right, the domain for this graph is all real numbers, except we have to skip the vertical asymptote. So the first vertical asymptote I see is at pi, and they repeat every 2 pi. They repeat every width of a period. And for this particular graph, the width of the period is 2 pi. So they start at pi and they repeat every 2 pi. So I have to skip pi, 3 pi, 5 pi, 7 pi, 9 pi, 11 pi, etc. The range for these graphs is the part that's easy. These graphs always go down forever, they always go up forever. So if I look for my y coordinates and say what y coordinates can you have, you're going to have all of them. So you're going to have negative infinity to positive infinity. Or if you wanted to match the notation to the range, or sorry, to the domain, then you could say that your range was just all real numbers. You could write that double bar R. So you could say all real numbers for the range as well. All right. Next, we're going to look at cotangent. So cotangent is very similar to tangent. We're going to start at 0 instead of starting at negative pi halves. You'll see in a second while we're doing that. And you'll notice that the graph is going to look very similar to tangent. So cotangent of alpha is x divided by y. And so if we look at 0, x divided by y is undefined. So there's our vertical asymptote. Pi fourths, x divided by y is 1. Pi halves, x divided by 1 is 0. 3 pi fourths, x divided by y is negative 1. And at pi, x divided by y is undefined. So there's our second vertical asymptote. So if we're graphing this one, if we want to compare it to tangent, when we looked at tangent, we had our first x-intercept at 0, and then an x-intercept at pi, and then 2 pi and 3 pi. And our x-intercepts ended up being on the pi's. And I'm going to show you. Just look back at our notes. Our x-intercepts ended up being right on the pi's. And then the vertical asymptotes were in between. This time, the vertical asymptotes end up being on the pi's. Vertical asymptote at 0, vertical asymptote at pi. So that's a little different than what we had with the tangent. All right, then we have the x-intercept at pi halves. And that's going to be the case for all of the halves. So at 3 pi halves, it would have been x divided by y. And then if we continue to look at the coterminal angles, 5 pi halves would have been 0. 7 pi halves would have been x divided by y, that's 0. 9 pi halves, x divided by y, that's 0. So all of the x-intercepts are at the halves. And then the other difference between cotangent and tangent is that pi fourths is a positive 1, 3 pi fourths is a negative 1. So here, pi fourths is right here, this is a positive 1. 3 pi fourths is right here, that's a negative 1. And so whereas tan slanted up towards the right, cotangent slants down towards the right. But otherwise very similar. So we can use similar strategies. All right, so here, if we were to find the domain, we would say, all right, our first vertical asymptote is at 0, and then at widths of pi after that. So I'm going to say the domain is all real numbers, but x cannot equal 0 plus pi k. So start at the first vertical asymptote and then the width of the period. Okay, so let's go ahead and try a transformed function. So we have negative 1/2 cotangent of 2x plus pi halves. So I'm going to go ahead and factor the inside of this. So I have negative 1/2 cotangent. And then I have to divide out the 2. Pi halves divided by 2 is pi fourths. So I'm going to be shifting the graph to the left pi fourths. So I have to be careful about that. Okay, so when I first start this, I know that this graph is going to be upside down, and it's going to have a vertical compression of 1/2. And so what I did is I went ahead and I made my labels, instead of going 2, 4, I made my labels 1, 2. I also noticed that there's a 2 for the b value. So the period of the graph is pi divided by b, which makes the period of the graph pi halves. And so the other thing I did is I made these intervals pi halves and pi instead of pi and 2 pi. So I made this graph a little bit, the interval's a little bit wider. So the period is pi halves, the frequency is 2. I'm going to have 2 curves between 0 and pi instead of just 1 curve between 0 and pi. Okay, so what I'm going to do is, just like I did with sine and cosine, I'm going to sketch out the portion of the graph that has the negative, the portion of the graph that has the vertical compression of 1/2, and the portion of the graph that has the period of pi halves. I'm going to do that first, and then when I'm done doing that, I'm going to take the graph and shift it to the left pi fourths. Okay, so I'm going to go back and label my notes a little bit more so that I do not feel as confused, okay, because I think some labels will be helpful. So in here, I'm going to write there are x-intercepts. I'm back on the tangent page. X-intercepts at ends of period, and then the curve goes up. This is normal. This is my little hint to myself, okay? And then for cotangent, the vertical asymptotes are at the ends of the period. And this graph, drawing it down, this graph slants down to the right. So this is going to help me to not get tangent and cotangent as confused. Okay. So I need to have vertical asymptotes, and I'm going to draw them lightly because I'm going to have to move them. So at 0 and pi halves and pi, I'll just draw a couple, okay? So at pi halves, and then my x-intercepts are going to be in between, okay? And normally my curve would go like this, and normally I would do 1 and 1. However, instead, I have to compress the graph to 1/2, and I have to create the negative version. So instead of starting at 1 and going up on this side, I'm going to have to start at 1/2, and I'm going to have to go down instead. So I'm going to be here, and then instead of going down and having 1 down here, I'm going to have to go up, and it's going to have to be 1/2 instead. And I'm not going to draw the curve. Okay, so 1/2, 1/2. Okay, now what I need to do to this entire part that I just drew lightly is I need to shift it to the left pi fourths, which is 2 boxes on the scale that I drew. Pi halves is 4 boxes, so pi fourths is 2 boxes. And as I do that, I'm just going to make it darker. So there's my dotted line. 2 boxes, 2 boxes, 2 boxes. There's my first one. 2 boxes, 2 boxes, 2 boxes. There's my second one. So my dotted lines are at pi fourths. Well, either way, they're in between my markings. So there I go. And then there's this. I'm not going to go all the way across my graph this time. I'm just going to draw 4 of these curves and call it good. There we go. So it's been reflected. I can tell it's been reflected because it's the opposite. It's going the opposite direction of the parent graph. Instead of going up to 1, it's going up to 1/2. And then I shifted all my points 2 boxes to the left. Okay, so my domain here is all real numbers. My first vertical asymptote, this is pi halves, so my first vertical asymptote is at pi fourths, so x cannot equal pi fourths plus pi halves k. So pi fourths, and then this is a width of the period, pi halves. And the range, it goes down forever and up forever, so all real numbers, or you could say negative infinity to infinity. Okay. For cosecant and secant, you'll either love them or hate them. These are they're weird, but I don't know. You'll love them or hate them. That you could think they're easy, you could think they're difficult. So cosecant, excuse me, is the reciprocal of sine And the easiest way to draw this is to draw a sine curve first. So that's where you might love it or hate it, is because it's like, oh, I just got to draw a sine curve to start with, and that's, you know, kind of a great place to start. So I'm going to draw the sine curve. So typical sine curve, I start at 0, I end at 2 pi at 0, I have 0 in the middle. And I'm drawing this lightly because this is not the answer for what cosecant is. This is just going to help me graph it. Between 0 and 0, I go up to 1. I go down to -1. So there's my sine curve. And I'm just going to keep doing that. There's my sine curve. Doing it lightly because this isn't my actual answer for what the graph is supposed to look like. Okay, now this is how you draw cosecant. Every place where sine has an x-intercept, cosecant would be undefined, because an x-intercept is an output of 0, and the whole number 0, if you write it as a fraction, is 0 divided by 1, and if you flip that, it's undefined. So anywhere that sine has x-intercepts, cosecant has vertical asymptotes. So these all become vertical asymptotes in the cosecant graph. So this is why I draw sine first, because once I draw sine, I know where to draw everything else. Okay, so that's where all the vertical asymptotes are. Then, any place that sine was 1, that's the fraction 1 over 1, and so the reciprocal of that for cosecant is still just 1 over 1. So that's actually part of the cosecant graph. So these points here, the positive one here and the negative one down here, those are part of the cosecant graph. And the way that the cosecant graph looks, I'm going to draw this dark because it's the actual cosecant graph, is they just look like they're sitting on top of the sine curve, or they're coming up from below the sine curve. They're just these little like bowl shapes, basically. And so this is why I draw the sine curve first. Because once you have the sine curve, you can draw your vertical asymptotes, and then you can draw these little bowl shapes, and then there's your graph. So technically, if I was being the most accurate, I should go through and erase this curve right here. Technically, that's what I should do. But I don't. I'm just going to leave it. That's me showing my work. Okay? So here, we can find the domain. The domain is going to be all real numbers. But x cannot be 0, plus, and then every pi, we have to skip the vertical asymptotes. So 0 plus pi k. Now, for this graph, we still have a period of 2 pi, because it takes 2 pi for the pattern to repeat. And the pattern is a bowl up top, a bowl below, up top, below, up top, below. So that's still a period of 2 pi. But the vertical asymptotes repeat every 1 pi. The range for this one is a little bit more exciting. We have from -infinity up to -1. So -infinity up to -1, including -1. And then from +1 up to infinity. All right, so that was cosecant. Let's try another cosecant. So this one has a stretch of 2. vertical stretch of 2, it's been shifted to the right pi halves and shifted up 1. So what we're going to do first is we're going to ignore the cosecant graph. We're going to draw the sine curve. So we're going to draw y equals 2 sine of x minus pi halves plus 1. We're going to graph this really lightly. And then once we're done graphing that, then we can go through and put the vertical asymptotes in and put the bols in. And then the bols and the vertical asymptotes are the cosecant graph. Okay, it's the easiest way to do it. So when I'm graphing sine, I know that my amplitude is 2. And I know that because there's no number in front of the x, that the period is just 2 pi. So I'm going to go ahead and start off by doing that. So 0 to 2 pi. 0 in the middle. My amplitude of 2 for the sine curve means that between the first 2, I'm going to go up 2. Between the first zeros, up 2. Between the second zeros, down 2. Okay, so here's my sine curve. And now I need to do the phase shift, and I need to move the graph up 1. So the phase shift tells me to take the point and move it to the right pi halves, which for this graph is 2 boxes, and then shift it up 1, which is for this graph 1 box. So shift it to the right pi halves and up 1 box. To the right pi halves and up 1 box. To the right pi halves and up 1 box. To the right pi halves and up 1 box. To the right pi halves and up 1 box. Okay, so there's my pattern for sine. And I probably could have made those dots a little bit lighter. Remember, I'm not actually graphing the curve right now. I'm making it easier for me to graph the curve. Okay, so here is my sine curve. Now I'm going to go through, and the places where the x-intercepts were, right here, this is where my vertical asymptotes go. Okay, and then once I have all my vertical asymptotes, I'm going to go through and put the bols in. Okay, so there's the cosecant graph. Secant is the exact same thing. Actually, hold on, let's not do secant yet. We have to find all the things. Okay, the period of this function is just 2 pi. We didn't change it at all because there was no b value. So the frequency is just 1 because the b value was 1. So it takes a width of 2 pi or a width of 8 boxes for us to get the top bowl and the bottom bowl. Frequency 1. The domain, all real numbers, x cannot be. And it looks like if this is pi and here's the asymptote is at pi halves. Pi halves plus, and it's a width of 4 boxes. the width of the vertical asymptotes, how far apart they are from each other, is always half of the period. So the period is 2 pi, so the width of the vertical asymptotes away from each other, they are pi away from each other. So domain, all real numbers, cannot have the first vertical asymptote plus the width of all the vertical asymptotes. So every pi, we're going to have to skip that value. The range is from -infinity up to -1, and from +3 to +infinity. -infinity up to -1, +3 to +infinity. Okay, now we can graph secant. So secant is just like cosecant, but instead of basing it off of a sine curve, you're going to base it off of a cosine curve. So this is the reciprocal of y equals cos. So I'm going to start with the cos curve. I'm going to start up at 1, end up at 1, dip down to -1 in the middle, cross 0, cross 0. Start up at 1, end up at 1, -1 in the middle, cross 0, cross 0. Start up at 1, end up at 1, dip to -1 in the middle, cross at 0, cross at 0. Okay, now just like the cosecant graph, all of the x-intercepts are going to become vertical asymptotes. Okay, and then from there, we'll go ahead and draw all the bowls in. Now, calling it a bowl is a Miss King term. Nobody else calls them that. I don't know what they actually call them. But that is not the correct mathematical term. That is just what they look like to me. Okay, there we go. So there is your secant curve or curves. So we have a domain here of all real numbers. X cannot equal pi halves plus pi k. So pi halves is the first vertical asymptote, and then they are a width of pi apart from each other. And then the range here is from -infinity up to -1, and then +1 up to infinity. Okay, I'm so sorry about this video, you guys. One last example. All right, to graph this with some transformations, we're just going to graph the cos function, and then we'll go through and we'll put the vertical asymptotes in and we'll put the bowls in. So we're going to graph y equals negative cos. I'm going to go ahead and factor out that 2 for the b value so I know what I'm graphing. And when I factor out the 2 pi thirds divided by 2 is just pi thirds. And so you can see that when I drew the axes ahead of time, since I knew I was going to be shifting this graph to the right pi thirds, I went ahead and I used 12 boxes here, so that I was choosing a number of boxes that could have pi thirds. as part of the labels, because doing 8 boxes or doing 4 boxes would have been difficult with the labels for me to then have to shift it pi thirds. So for cos, the amplitude is going to be 1. The period of the graph is going to be 2 pi divided by 2. So the period of the graph is going to be pi, so that's where we're going to get a whole curve, or that's where we're going to get 2 bowls. And the frequency is going to be 2. Okay, so since this is a negative cos graph, we're going to start at -1 and end at -1. So start at -1 and end at -1. So I'm doing a width of pi because the period is pi. In the middle, we're going to go up to +1. And then between those two, we're going to cross at 0. Cross at 0, cross at 0. Okay? And now that I have that in there, I've done the upside down portion, I've done the period change. Now I just need to take the graph and I need to shift it to the right pi thirds. And that shift to the right pi thirds is the equivalent of 4 boxes. So each of these points is going to go right 4 boxes. And then what I'm going to do is just continue the pattern. All right, so now I can go through and I can put the vertical asymptotes where all the x-intercepts are. And you can see they're just the point right in the middle. So if your graph is shifted up or down, you can still find it pretty easily where the x-intercepts had been. But in this case, they were still on the x-axis. And then I'm going to go ahead and do my bowls. All right, so here for the domain, the first vertical asymptote is just 1 box away. And since I had 12 boxes equaling pi, that means that 1 box away is pi twelfths. So 1/12, 2/12, 3/12, 4/12. 4 over 12 is 1/3. So this is 1/12 right here. So it's pi twelfths. Sorry, all real numbers x cannot equal. Gotta write it correctly. All real numbers x cannot equal pi twelfths. There we go. Okay, plus. And then the period is pi. So then it's every pi halves. Every 6 boxes from there is how often it repeats, which is half of the period. So every pi halves, k, is how often we're going to skip the value because of the vertical asymptote. The range here is -infinity up to -1, and then -1 up to positive infinity. All right, and then here we have, a little cheat sheet for you.